Alright everybody, so welcome back. This is lesson 21.2 on capacitance. It's a pretty short lesson, so we're going to jump right in. So a capacitor is a device that's used to store electrical charge, and the purpose of this is so that it can be quickly discharged. So like you want to build up a lot of charge on something and then be able to use it right away for whatever purpose it is. So some examples of capacitors that you might have be accustomed to or know about that use newer capacitors. So like a flash on a camera. So especially like the old, if you remember, if you're this old, or if you can remember disposable cameras. So like there was a flash where you would hold a button down and you would hear it charge up. So it would make like a high pitched frequency. And then when you pressed the button to take the picture, the flash would be released. So as you're pressing that first button down, you're storing the charge on in the capacitor, and when you depress the button to take the picture, you are releasing that energy. That energy flows out in the form of light, and you get a quick flash, so that energy is used up quickly. Defibrillators, much greater version of this. So when you have those two paddles, they're hooked up to a big battery. That battery charges those paddles up, and the purpose of the defibrillator is again to release that electrical charge quickly and hopefully shock a person's heart back into rhythm. Keyboards, so like the keyboard that you might type on, if you look, and you can't see this, but if you took apart a keyboard, every individual key has a metal plate on it, and there's another metal plate kind of sitting directly underneath it. And the space between that, what happens is the charge builds up on those keys, and when you press an individual key, it sends a signal. Like as you depress the key, the capacitor changes, so like the space between those plates changes, and it releases that energy and tells the computer that you want this type of symbol to appear on your screen. So those are some everyday kind of capacitors. They're in other devices as well, but those are the ones that you're probably most familiar with. So capacitors are the items, but they have capacitance, which is the ability of a capacitor to store electrical charge when a particular potential difference is present. So the symbol C stands for capacitance, Q is charge, just like we knew from previous lessons, and then triangle V is potential difference, or just potential, or generally I call that voltage. So it's just your charge per voltage. So the way this equation works, if you have a bigger charge, you would get a bigger capacitance. If you have a bigger voltage or potential difference, you would have a smaller capacitance with that same amount of charge. The unit for capacitance is something called a farad. So we're measuring farads, and a farad is a coulomb per volt. A farad is at a very, very large unit, so we use prefixes like micro, which is 10 to the negative 6, pico, 10 to the negative 12, nano, 10 to the negative 9. I didn't write, but that's another one. And if we were trying to measure the energy that's stored in a capacitor, it's equal to this equation. So it's 1/2 Q times triangle V, or the potential difference. There are other variations, because you can put in capacitance in here for Q, and C times V. So like you have lots of other equations, but generally if you know this equation and you know this equation, you can solve for everything you need. So I don't try to overcomplicate things. So in the book there are many other equations that you could use that are related to the energy stored in a capacitor based on these three factors. Okay, so that's what capacitance is, but it's also dependent upon the physical makeup of the materials that make the capacitor. So one of the most common capacitors that we'll talk about is something called a parallel plate capacitor. We'll have one of those in class. But the idea is like you have basically two metal plates, and they can be circular plates or rectangular plates. And based on the physical properties of how those plates are set up and what they're hooked up to, that's what determines the capacitance of that capacitor. So this is the equation for it. So it's E naught, which is something called epsilon naught, or the permittivity of free space. So it's just a value, it's a constant value number. So that's for normal free space in a vacuum. And we don't live in a vacuum, but air essentially behaves the same as a vacuum, so we just use that number. A is the area of those plates, so it's how big the plates are. So if we had, there we go. If we had a rectangular shaped plate, if that's the one plate and this is the second plate of the capacitor, the area of the plate, kind of the length times the width, is what we would use. If it was a circular type plate, we would need R, and we'd do pi r squared. So again, if the area increases, you can have a bigger capacitance because you can store more charge. That's essentially what it is. So if you had, if the circle goes from a smaller circle to a larger circle, there's a bigger area, which means you can fit more charge per voltage. The other thing that they measure is the separation between those plates. So if like these are the two plates, one's positive and one's negative when you hook it up to the battery. So if I hook this up to a battery, and I'll draw a quick battery here. So if this is a battery, we have the positive side of the battery and the negative side of the battery. We talked about this in a previous class, and a parallel plate setup. But the separation between those, they call D, and we used that when we were measuring the electric field in a parallel plate capacitor. But this also has an impact on the capacitance. So the smaller, or if you increase this distance, the capacitance goes down. So they're inversely related. E naught is just a constant, though. That doesn't change. So that's basically the physical properties that determine how much capacitance is there. The capacitance is also dependent by, it's like a ratio of charge per voltage. So Q over V, or potential difference. So like if you have a bigger voltage, you should be able to get a bigger charge, because the capacitance is a constant because it's dependent upon these factors. So it's the physical factors that impact and make the capacitor what it is, and then depending on what kind of battery or voltage potential difference you have hooked up to it, that'll determine how its charges on those individual plates. So you have charge Q that gets stored on these plates. So you get positive charges on one plate and you get negative charges on the other. All right, so let's go ahead and go through a problem using those formulas. So it says, for part A, what is the capacitance of a parallel plate capacitor with metal plates, each of area 1 meter squared, and they're separated by 1 millimeter of separation. So we're going to use that last equation that we just had. So part A, C is equal to epsilon naught times A divided by D. So epsilon naught is a constant, so that's 8.85 times 10 to the negative 12th. Again, you will have that on your test. You won't have to have that memorized. The area is just 1, so it says the area is just 1 square meter, so we'll use that. And then the separation is 1 millimeter. We don't work in millimeters, so we're going to divide by 1 times 10 to the negative 3rd, because 10 to the negative 3rd is what milli stands for. So if we do this in our calculator, you get 8.85 times 10, and it'd be the negative 9th farads. So F farads for capacitance. If you wanted to write it in a different unit, it'd be like 8.85 nano farads, because nano is times 10 to the negative 9th. So that's part A. Part B wants to know how much charge is stored if it's hooked up across a 3,000, 3 times 10 to the third is 3,000 volt battery. So this is where we're going to use C equals Q over V, or delta V if you want to do it that way. And we're going to solve for Q. So if we rearrange this, it'd be Q is equal to the capacitance times the voltage, or potential difference. So it'd be that 8.85 times 10 to the negative 9th times the voltage, which is 3,000 volts. And if you multiply those together, you get something like 2.655 times 10 to the negative 6th, and that would be coulombs. And that's a pretty normal amount of coulombs, because we said 1 coulomb of charge is a really big number, so this is like microcoulombs. For part C, I asked how much energy was stored here. So energy in a capacitor is 1/2 QV. So we know Q, we know V, so we just have to plug into those two things and then divide by 2. So it'd be 1/2. Q is our value that we just got for that answer, so 2.655. times 10 to the negative sixth, and then we're going to multiply that by 3,000 volts, and you should get a pretty small number, 0.004 joules. So not a large amount of energy on this, probably because the capacitance is a pretty small number in this value. So it's not a very big capacitance, even though you're hooked up to a fairly large voltage. So that's the answer for that last piece there. All right, so so that's just like a single capacitor, or capacitor when it's just a single item. In circuitry, we have I was skipping over part. In circuitry, we have more than one capacitor, so we'll get to that when we have multiple capacitors, what to do. But another idea, which is really common in construction with capacitors, is something called a dielectric. So a dielectric is basically when an insulating material is placed between the plates of a capacitor to reduce the separation between the plates. So if you think about a capacitor, again, if we have, like, this is one plate, and I'll call that one the positive one, and a negative plate over here. If you have a big enough charge here and they touch, obviously they're going to discharge, and you wouldn't have that separation of charge, which is what you need to have capacitance. So what they do, again, to increase capacitance, basically we said that we want these to be as close as possible. But as they get closer and closer together, there's this more likelihood of charge jumping from one to the other. So what they do is they put an insulator between it. So they get the two plates really close together. So I'll just draw like a very small gap between that. And they put in this insulator. So they put in this material, a very thin material of insulation, which I drew in blue here, to prevent the charge from being able to transfer from one plate to the other. So the charge stays where it's supposed to stay. So that's like one thing that they try to do to protect the capacitor. Another benefit of this is that it actually increases the capacitance. So like if you have a dielectric in there, you can increase the amount of capacitance that you can store on that capacitor. So this capacitance, or the dielectric value, is just a number times, it's called K. It's really like a kappa, it's a lowercase kappa, but it's the dielectric constant. So that's just a number that would be given in a problem, or you'd be solving for it. Like you compare it, like the capacitor, if there was no dielectric, to what it was, and then you can, like, what the capacitance was, and you could solve for K. So it's still epsilon at not A over D, it's just now you have this capacitor or dielectric in there, so that's where that kappa value comes from. So not that big a deal, but it's kind of a real thing that happens. So now I'm going to get into when you have several capacitors. So often you have more than one capacitor connected together, and a group of capacitors will act as one, they work together as one capacitor with what's called equivalent capacitance. So equivalent capacitance is this idea CEQ. So the equivalent capacitance depends on two things. One thing it depends on is the individual capacitors that are connecting to it, so the physical makeup and values for those ideas. And it also depends on the way they're connected. So we're going to look at series and parallel connections in lots of different circuits. So we're going to start with this with capacitors first. We'll get into resistors next, so that'll be in one of the upcoming lessons. So in capacitors, and this is kind of showing you the idea in series. Series means one after the other, or like in a row in sequence. So like if you look at this is our battery, and then we have three capacitors: capacitor 1, capacitor 2, and capacitor 3, and they're all kind of hooked up in a line. So again, in a capacitor there's space in between, so that's why there's just a gap there. But what happens is, essentially, the more capacitors you put in here, you increase the separation value, or D. So as you increase the separation value D, based on our equation, C equals epsilon naught A over D, as you increase this separation, the capacitance goes down. So they decrease. So the more capacitors you have in a row in series, the smaller the total or equivalent capacitance is. So this is the equation that relates them. So it's an inverse, kind of like 1 over C1 plus 1 over C2 plus 1 over C3. C1, C2, and C3 are the individual capacitances of the individual capacitors you're connecting in series. And then CS is like that equivalent capacitance. So you would take the inverse of each one of these, add them together, and then you have to flip it over at the end. So if you wanted CS, the capacitor of a group of, or the equivalent capacitance of a group of capacitors in series, it would be 1 over C1, that number, plus 1 over C2, whatever that value was, plus 1 over C3. And then you would take that answer and raise it to the -1 power, or take the inverse of it. And that's what you'll get for the capacitance equivalent. Okay. In parallel, it is the reverse idea. So again, essentially, we're looking at capacitance is epsilon naught A over D. So when you have capacitors in parallel, parallel means that, and you can see these kind of look parallel to each other, there's more than one path. So there's an individual connection between each capacitor and the battery. So if I draw kind of the path here, like there's a path for each of these three capacitors to be hooked up to the battery. So they're like individually hooked up. And what you're doing essentially in that setup is that you are increasing the area of the plate. So like you're having a larger total area because you're taking this area and this area and this area and kind of putting it together to get a bigger set of plates. So the bigger the area, the bigger the capacitance. So that's the relationship there. So as the area increases, the capacitance should increase. And the equation for that is really simple. You just add them together. So you just take the capacitance of each individual one, add them together, and that'll be the equivalent capacitance CP. So you don't have to do a ton of math with that. So let's just practice that, and that'll be the last thing in this video. Okay, so I misread these, so let me go back. So we're going to try to figure out the capacitance for these three capacitors, a 1, a 5, and an 8 microfarad capacitor. We're going to put them together in series for this one, and we're going to put them in parallel for this one. So let's do the parallel first, because parallel is easier. So capacitance and parallel, the equivalent capacitance would just be you add, so it'd be 1 plus 5 plus 8. So that just gets you 14, and the unit would be micro farads. Because all of them are micro, you don't have to convert anything. If this was micro and this was milli and this was nano, you'd have to convert all of them to a common one and then get the answer. For series, it's a little bit more challenging. So it would be the inverse, so it would be 1 over 1 plus 1 over 5 plus 1 over 8. And then you take the inverse of all those. I just used the calculator and did it. So this turns out to be, once you add them, flip them, add them, and then take the inverse, you get 0.755, and it's microfarads because that's the same unit for all of them. So looking at this again, we expected if it's in series, we have a bigger separation, so the capacitance should be less. So this value is smaller than any of the individual ones. And then in parallel, in capacitors, they add together to get you a bigger capacitor because you're increasing the total area. So if you add these together, 14 is larger than any of the individual ones. So you can use that to help you check. So that's the end of section 21.2, which is dealing with capacitance. The next video will deal with resistors and current and voltage.